Every river, every bolt of lightning, every galaxy in the sky shares the same hidden skeleton, the same branching shape, the same invisible geometry. Scientists are now finding a pattern so consistent and so precise it appears from the scale of atoms to the very edge of the observable universe. We will visit the structure that mirrors a human brain, the number that keeps showing up where it has no right to be, and the discovery that may change everything we know about reality itself. If you enjoy this journey, like and subscribe. Let's begin. In 2020, a neuroscientist and a cosmologist sat down together and compared two images side by side. One showed a slice of brain tissue under a microscope, with neurons branching and connecting across a pale background. The other showed a map of the known universe drawn from telescope data collected over 2 decades. They expected some loose visual similarity. What they found instead shook both of them. The two images were nearly identical. Filaments stretched between glowing clusters, nodes lit up at every major intersection. Dark, empty spaces sat between the structures with almost the same proportion in both images. The branching angles were similar. The density of connections per region was similar. When the team ran a statistical comparison, measuring the actual mathematical structure of both networks, the numbers matched in ways that went far beyond coincidence. The universe, mapped at its largest scale, looks like a brain. The cosmic web is the name scientists give to the full structure of matter across the universe. It is made of galaxy filaments, long thin threads of gas, dark matter, and galaxies stretched across hundreds of millions of light years. They connect at massive hubs called galaxy clusters, which contain thousands of galaxies packed together. Between the filaments sit enormous empty regions called voids, some stretching over 300 million light years across. Your brain, by comparison, is roughly 6 inches wide. Its neurons form their own web of filaments, connecting at nodes, leaving dark gaps between them. The structures operate at scales so different they should share nothing in common. The forces that shape them are completely different. Gravity builds the cosmic web over billions of years. Electrochemical signals build neural networks inside a skull over decades. There is no physical reason these two systems should look the same. And yet they do. The 2020 study, published by Franco Vatsa and Alberto Filetti, calculated that the cosmic web and the human cerebral cortex share a similar clustering coefficient, a measure of how tightly connected nodes are to their neighbors. They also found similar spectral density curves, which describe how structure is distributed across different scales. The similarity held up across multiple types of measurement. This raises a question the study itself could not answer. Is this a coincidence? A result of two very different systems following the same mathematical rules? Or is there something deeper at work, some organizing principle that shapes structure wherever energy and matter flow together? Scientists lean toward the second explanation. Networks that grow by connecting their most connected nodes tend to produce similar geometries, regardless of the medium. This pattern is called scale-free network behavior. Social connections, internet links, power grids, and blood vessel systems all show it to varying degrees. The universe and the brain may simply be two very large examples of a pattern that nature defaults to whenever complexity is allowed to grow freely. Here is what makes this harder to dismiss. The similarity is measurable. It holds up under math, not just under a quick visual impression. And the more precisely we map the cosmic web, the clearer the resemblance becomes. Whether that means anything profound, no one can say yet. What it does confirm is that the universe organizes itself in ways that repeat across scales that have no business resembling each other. And the brain-universe comparison is only the beginning of the pattern. Look at a river delta from above. Now look at the inside of a lung. Now look at a bolt of lightning frozen in high-speed photography. Now pull back to a map of galaxy filaments spreading across 1 billion light-years of space. The shape is the same. Each system branches from a central point into progressively smaller and thinner arms. Each arm splits again, then again. The angles change slightly each time, but the branching ratio, how much thinner each new branch is compared to the one before it, stays remarkably consistent. Scientists call this a dendritic pattern, from the Greek word for tree. The reason dendrites appear in so many different systems is surprisingly simple. Branching is nature's most efficient solution to the problem of distributing or collecting something across a surface or a volume. A river needs to drain water from a wide landscape into a single channel. A lung needs to deliver air to every corner of tissue. A lightning bolt needs to find the fastest path for electrical charge to travel through uneven air. A galaxy filament needs to funnel gas and dark matter toward the densest hubs. Different problems. Same answer. Leonardo da Vinci formalized this most clearly, centuries before anyone had tools to prove it rigorously. He observed that, when a tree branch splits, the cross-sectional area of the two new branches adds up to the cross-sectional area of the original branch. This preserves the flow. Too little branching and the system bottlenecks. Too much, and it wastes material building infrastructure that carries almost nothing. Modern science confirmed his observation. Biologists call it Murray's Law when applied to blood vessels. Engineers use the same principle when designing efficient pipe networks. And the cosmic web, shaped entirely by gravity and the pressure of dark matter, follows a version of this same constraint, without any blueprint to follow. That last part is what stops physicists. Rivers are shaped by the terrain they carve. Lungs are shaped by evolutionary pressure over millions of years. Lightning follows the physics of electrical discharge through a specific medium. The cosmic web is shaped by nothing more than gravity acting on quantum fluctuations from the early universe. It had no model to copy. It had no organisms selecting for efficiency. And yet the branching pattern emerged anyway. One way to think about this is through the lens of optimization. Any system that needs to move energy or matter across space, while minimizing waste, will tend to arrive at branching as a solution. The universe may be doing something that looks like optimization without any optimizer present. Structure arises because certain shapes are simply more stable, more efficient, and more resistant to collapse than others. Some researchers push this further. They argue that branching is a deep geometric attractor, a shape that physics and math together make inevitable under a wide range of conditions. If true, it means the universe does not accidentally resemble a lung or a river delta. All of these systems are drawing from the same geometric well, the same hidden template. What makes that idea difficult to shake is that the branching pattern is measurable, not vague or approximate. When measured carefully, the ratios hold, the angles cluster. The statistics match in ways that coincidence alone does not explain. And branching is only one piece of this pattern. The next piece is a number, a very specific, very stubborn number that refuses to stay where it belongs. Count the spirals on a pine cone. Start with the spirals curving one direction, then count the ones curving the other. Almost always the two counts are consecutive numbers in the Fibonacci sequence: 8 and 13, 13 and 21. The arrangement is so consistent that botanists use it as a diagnostic tool. Now look at the arms of a spiral galaxy. The curve each arm follows is called a logarithmic spiral. The ratio at which the spiral expands outward as it turns is deeply connected to the same sequence. The same spiral shape appears in nautilus shells, in the arms of hurricanes, in the seeds of a sunflower, and in the curl of a wave just before it breaks. The Fibonacci sequence starts simply: 1, 1, 2, 3, 5, 8. 13, 21. Each number is the sum of the two before it. As the sequence grows, the ratio between any two consecutive numbers approaches the golden ratio, approximately 1.618. This ratio appears so often across biology, geometry, and cosmology that mathematicians have studied it for over 2,000 years. But why does it keep showing up? In plants, the answer involves growth efficiency. When a plant produces new leaves or seeds, it wants to avoid stacking them directly above each other, so every leaf can catch sunlight and every seed can spread without crowding. The angle that best achieves this is approximately 137.5 degrees, called the golden angle. Produce leaves at that angle repeatedly, and Fibonacci spirals emerge automatically. No instruction required, just geometry doing its job. In galaxies, the explanation is more complex and still partly debated. Spiral arms do not rotate like rigid structures. Individual stars orbit the galactic center at different speeds. What holds the spiral shape in place is a density wave, a slow-moving region of compressed gas and stars that persists even as the individual members of that region keep changing. The logarithmic spiral that results from this process naturally produces angles consistent with the golden ratio. In hurricanes, the same logarithmic spiral emerges from the interplay of rotation and radial airflow. The mathematics of a rotating fluid under pressure is different from the mathematics of a galaxy, which is different again from the mathematics of plant growth. Yet the spiral is the same. This is measurable, not mystical. The golden ratio and Fibonacci spirals are geometrical solutions that keep appearing because they represent efficient, stable configurations. Wherever nature needs to pack, grow, rotate, or flow, while minimizing waste and maximizing coverage, it tends to land on the same shapes. What makes this genuinely strange is the precision. The golden ratio does not appear as a rough approximation. It appears as a measurable constant, within observational error, in systems that have never interacted with each other. A galaxy cluster and a pine cone have never exchanged information. They have never been subject to the same evolutionary pressure. They are separated by almost incomprehensible differences in scale and material, and they share the same spiral. One way to interpret this is that the universe has a preferred geometry, a set of shapes it returns to again and again across every scale and every medium. The Fibonacci spiral is one expression of that preference. But these are surface features. Underneath them sits something far harder to explain, a set of numbers so precise, so finely adjusted, that changing any one of them even slightly would mean none of this ever existed. Physics runs on a small set of numbers: the strength of gravity, the charge of the electron, the mass of a proton, the speed of light, the cosmological constant which governs how fast the universe expands. These are called the fundamental constants of nature, and every physical law we know depends on them being exactly what they are. Change any one of them slightly, and reality falls apart. If gravity were slightly stronger, the universe would have collapsed back on itself within seconds of the Big Bang. No galaxies, no stars, no anything. If gravity were slightly weaker, matter would never have clumped together at all. The universe would be a thin, cold, expanding fog. If the strong nuclear force, the one that holds atomic nuclei together, were about 2% weaker, protons and neutrons would not bind to each other. Atoms beyond hydrogen would be impossible. No carbon, no oxygen, no chemistry, no life. If the strong force were slightly stronger, protons would fuse into nuclei of 2 protons, burning through all hydrogen in the early universe and leaving nothing for stars to run on for billions of years. The fine structure constant, which governs how electrons and light interact, appears to be tuned to allow chemistry to function. If it were significantly different, atoms could not form stable bonds. The periodic table would be useless. Molecules could not exist. These are confirmed numbers. Physicists have run the calculations, and the margins are extraordinarily thin. The cosmological constant alone, which governs the rate of universal expansion, appears to be fine-tuned to a precision of roughly 1 part in 10 raised to the power of 120. That is a 1 followed by 120 zeros in the denominator. The universe should not look like this. Random processes do not produce that kind of precision. If the constants were selected by chance, the odds of getting a universe capable of forming atoms, let alone stars, let alone life, are so small they are effectively impossible by any intuitive measure. 3 competing explanations exist, and none of them is simple. The first is that the constants are mathematically necessary. Some future theory may reveal that the numbers we observe are the only numbers that are mathematically self-consistent. If any other values led to logical contradictions, only this particular set would be possible. The second is the multiverse. If an enormous or infinite number of universes exist, each with different constants, then it is not surprising that at least one has values compatible with complexity. We happen to live in one that works because only in such a universe could observers exist to ask the question. The third is the most uncomfortable. The constants were set deliberately. Most physicists resist that third option because it lies outside the reach of any experiment. You cannot test for a designer. But the precision is real, and the question it raises does not go away simply because the answer is inconvenient. The universe contains hidden patterns in its geometry. The numbers that generate all of physics appear to be tuned in a way that allows those patterns to exist at all. And in the next chapter, the strangeness deepens, because a team of scientists recently tried to measure exactly how similar the cosmic web is to a neural network, and what they found forced them to revise their own expectations. Franco Vatsa is an astrophysicist who studies the cosmic web. Alberto Filetti is a neuroscientist who studies the human cerebral cortex. In 2020, they published a paper together that most scientists in their fields did not expect to take seriously. The title asked whether the universe and the brain were more similar than they appeared. The answer, backed by statistical analysis, was yes. The study went further than a visual comparison. Vazza and Filetti did not just look at the two systems and note that they seemed to branch in similar ways. They measured specific mathematical properties of each network and compared the numbers directly. One property they measured was the clustering coefficient. This describes how tightly connected a node is to its neighbors. A high clustering coefficient means that if you are connected to node A and node B, there is a good chance A and B are also connected to each other. In the cosmic web, galaxy clusters act as nodes, and filaments act as nodes, and synapses act as connections. Both networks showed similar clustering coefficients across multiple spatial scales. Another property was the spectral density curve. This describes how structures of different sizes are distributed across the network. A flat curve means structure is spread evenly at all scales. A steep curve means most structure is concentrated at one scale. Both the cosmic web and the cerebral cortex showed nearly identical spectral density curves, meaning they are structured similarly, not just at one scale, but across a range of scales simultaneously. The two systems also showed similar ratios of nodes to connections, similar void space distributions, and similar trends in how connectivity changes as you zoom in or out. These are numbers that matched. The study was careful to state what this does not mean. The cosmic web and the human brain are made of completely different materials. They formed through completely different timescales. One spans billions of light years. The other fits inside a skull. The similarity does not suggest any direct physical connection between them. What it does suggest is that both systems are governed by the same class of mathematical rules. Rules about how networks grow when nodes attract more connections the more connections they already have. rules about how structure distributes itself through space when energy flows along paths of least resistance, rules that appear in social networks, in ecosystems, in the internet, and apparently in both the largest and one of the most complex structures in the known universe. The study sparked a small controversy. Some researchers argued the comparison was superficial. Others pointed out that visual similarity between networks is common and not necessarily meaningful. But the statistical measures Vasa and Folletti used were designed specifically to go beyond visual impression. And those measures held up. What lingers is a question the study could not answer. If two systems as different as a galaxy network and a neural network share this much mathematical structure, how many other systems share the same underlying rules? How deep does the pattern go? And if the rules are that universal, do they belong to physics at all? Or do they belong to something more fundamental? Mathematics, perhaps. And that connection between math and the physical universe is one of the strangest puzzles in all of science, because math was invented by humans to describe things they had already observed. So why does it keep predicting things before anyone has ever looked? Break off a piece of broccoli. Look at the piece. It resembles a smaller version of the whole head. Break off a smaller piece from that. Same shape again. Keep going down to the scale your eyes can resolve. And the pattern keeps repeating. The branching structure at every level mirrors the structure above it. This is a fractal, a shape that repeats itself at every scale. The mathematician Benoit Mandelbrot formalized the idea of fractals in the 1970s, though the patterns had been observed in nature for centuries before anyone had language for them. Mandelbrot showed that many natural shapes are self-similar, meaning pieces of the whole resemble the whole itself. Coastlines, mountain ranges, snowflakes, river networks, blood vessel systems, and lightning bolts all showed fractal properties. Then scientists pointed their tools at the universe. The distribution of galaxies across space turned out to be fractal up to a certain scale. Galaxies cluster. Clusters of galaxies cluster again into superclusters. Superclusters arrange themselves into filaments and sheets. The pattern repeats, each level containing smaller versions of the structure above it. This fractal behavior holds up to scales of roughly 300 million light years, beyond which the universe begins to look roughly uniform. That upper limit is important and still debated. If the universe were fractal at all scales without limit, it would violate the cosmological principle, the assumption that the universe looks the same in every direction when viewed at large enough scales. The fact that the fractal ends at a certain point suggests the pattern has a ceiling, which itself raises questions about what mechanism imposed it. Fractals arise from simple repeated rules. The fractal dimension of an object measures how completely it fills the space it occupies. A line has a dimension of 1. A solid square has a dimension of 2. A coastline, which is too jagged to be a smooth line but does not fill a surface, has a fractal dimension somewhere between 1 and 2, often around 1.2 or 1.3. The cosmic web has a measured fractal dimension of approximately 2.2 at the scales where it behaves fractally. This means it fills three-dimensional space in a way that falls between a two-dimensional sheet and a three-dimensional solid, thin enough to leave enormous voids between its filaments, but structured enough to concentrate most of its matter along specific paths. What makes fractals more than a visual curiosity is that they reveal the process that created them. Self-similar structure at multiple scales is the signature of a recursive process, one that applied the same rule over and over. In the universe, gravity is that rule. Gravity attracts mass to mass. That clumping attracts more mass. The process repeats at every scale gravity can reach, but fractals do not explain themselves. Knowing that a rule repeats does not tell you why the rule exists in the first place, or why that particular rule produces the specific geometry that appears from snowflakes to superclusters. Mandelbrot once said that clouds are not spheres and mountains are not cones. He meant that nature does not follow smooth, simple geometry. It follows a rougher, deeper kind of order that classical mathematics could not even describe until the 20th century. The universe is rougher and more ordered than anyone expected. And the next chapter takes that roughness even further back, to the very first light the universe ever released, and the pattern already written into it before a single star was born. About 380,000 years after the Big Bang, the universe cooled enough for electrons and protons to combine into neutral hydrogen atoms for the first time. Before that moment, the universe was a hot plasma, opaque and glowing. The moment it cooled enough for atoms to form, light was released across all of space simultaneously. That ancient light is still traveling today. We call it the cosmic microwave background. Every direction you point a sensitive enough detector, that light is there. It fills the entire sky at a temperature of roughly minus 455 degrees Fahrenheit. A whisper above absolute zero. But it is not perfectly uniform. Tiny temperature variations exist across the sky. Differences of about 1 part in 100,000. Some spots are very slightly warmer, others are very slightly cooler. These ripples are a map of the structure of the early universe, imprinted in light, preserved across nearly 14 billion years. Quantum mechanics predicts the size and distribution of these ripples from first principles. The same theory that describes how electrons behave inside an atom also predicts the pattern of temperature variations in the oldest light in the universe. When satellites measured those variations with high precision, what they found matched the quantum predictions almost exactly. The match was precise. The power spectrum of the cosmic microwave background, a mathematical description of how much variation exists at each angular scale, fits the theoretical prediction down to statistical precision. Scientists use it as one of the most precise confirmations of both quantum mechanics and the theory of cosmic inflation ever achieved. Cosmic inflation is the idea that the universe underwent an enormous burst of expansion in the first tiny fraction of a second after the Big Bang, stretching microscopic quantum fluctuations up to cosmic scales. Those fluctuations, quantum mechanical in origin, became the seeds of all structure. Every galaxy, every cluster, every filament in the cosmic web grew from those initial variations. Quantum mechanics, the physics of the very small, directly caused the structure of the very large. That sentence is worth sitting with. The pattern in the cosmic microwave background is a quantum pattern. The cosmic web is its grown-up version. The same physics that governs the behavior of a single atom also shaped the arrangement of every galaxy in the observable universe. The connection was measured when the Wilkinson Microwave Anisotropy Probe and later the Planck satellite mapped the cosmic microwave background with increasing resolution. The theoretical curves and the observational data aligned in ways that left very little room for alternative explanations. Physicists described the agreement as stunning, some of the most precise measurements in all of science. But precision creates its own mystery. The quantum fluctuations that seeded all structure were random variations, probabilistic by nature. Yet the universe that emerged from them is full of ordered patterns, repeating structures, mathematical regularities. How does randomness, at the smallest scale, produce such deep order at the largest? That question has no clean answer yet. What it does have is a number that keeps appearing inside the answer, regardless of which direction scientists approach it from. A number showing up in cicada survival strategies and in atomic energy levels, separated by billions of years, and a scale difference that should make any connection impossible. Every 13 or 17 years, the ground of the eastern United States erupts with cicadas, billions of them. The emergence is synchronized across enormous regions, with different broods appearing on their own precise schedule. The broods that have lasted longest through evolutionary history are the ones operating on 13-year and 17-year cycles. Both 13 and 17 are prime numbers. This is survival mathematics. A prime number is divisible only by itself and 1. That property makes it extremely difficult to synchronize with other numbers. If a predator species has a population cycle of 2, 3, 4, or 6 years, it will rarely align with a 13 or 17-year cycle. The cicadas surface when their predators are not numerically primed to spike. Evolutionary pressure selected for prime number emergence because prime numbers are the least predictable, the hardest to overlap with. Life discovered number theory through natural selection. Now shift from the forest floor to the inside of an atom. When an electron in an atom absorbs or releases energy, it jumps between energy levels. These levels follow discrete, quantized patterns described by quantum mechanics. The spacing between energy levels in certain atoms, particularly in the nucleus, follows statistical distributions that physicists call the Gaussian unitary ensemble. In the 1970s, a mathematician named Hugh Montgomery was studying the spacing between prime numbers along the number line. He met the physicist Freeman Dyson at a conference. Dyson looked at Montgomery's spacing formula and immediately recognized it. The distribution of gaps between prime numbers matched the distribution of energy level spacings in heavy atomic nuclei. Exactly. The connection is now called the Montgomery-Odlyzko law and is one of the most mysterious correspondences in all of science. Prime numbers are abstract mathematical objects with no physical component. Atomic energy levels are measured in laboratories using real atoms. There is no known reason these two things should share the same statistical fingerprint. Both follow a repulsion rule. Primes tend to avoid being too close together on the number line beyond a certain scale. Energy levels in quantum systems tend to repel each other, spreading apart rather than clustering. The repulsion is quantitatively similar in both cases, measured by the same type of distribution function. Mathematicians have not proven why this connection exists. Physicists have not found a physical mechanism linking number theory to quantum structure. The correspondence simply appears when both systems are measured carefully enough. What this suggests is that prime numbers, the most fundamental objects in mathematics, may be woven into the fabric of physical law at a level deeper than any current theory can reach. The universe organizes its energy levels the way mathematics organizes its most irreducible numbers. Some researchers believe this connection is a clue pointing toward a unified framework where the structure of mathematics and the structure of physics are the same thing viewed from different angles. That framework does not exist yet, but the clue is there, measured and confirmed, sitting at the intersection of number theory and quantum mechanics. Cicadas found the primes through evolution. Atoms inhabit the primes through physics. Somewhere in that strange agreement is a signal that the pattern connecting these systems runs deeper than biology or chemistry or quantum mechanics can individually explain. And if prime numbers appear in atomic physics, it raises the question of what other mathematical constants have found their way into the structure of physical reality. One of them appears everywhere, from the spin of black holes to the petals of flowers, and it has a very specific name. The golden ratio is approximately 1.618. It has been known since ancient Greece. It appears when you divide a line into two segments, such that the ratio of the whole line to the longer segment to the shorter one. The result is a self-consistent proportion, one where the ratio reproduces itself regardless of scale. For centuries it was treated as an aesthetic ideal, a mathematical curiosity that architects and artists explored. Then scientists began finding it in places that had nothing to do with art. Saturn's rings are divided by gaps created by gravitational resonances with the planet's moons. The most prominent gap, the Cassini division, sits where a particle's orbital period would be exactly half that of the Moon, Mimas. But when researchers mapped all major resonance gaps in Saturn's rings, the ratios between their positions showed clustering near values connected to the golden ratio. The ring system organizes itself under the influence of gravity alone into spacings that echo the same proportion found in a Nautilus shell. Spin is measured differently for black holes. A black hole's spin is described by a parameter that runs from 0 for a non-rotating black hole to 1 for a maximally spinning one. Observations of stellar mass black holes and supermassive black holes have shown that many spin at rates where the ratio between their angular momentum and the theoretical maximum clusters around values related to the golden ratio. Researchers studying X-ray binary systems have noted this pattern across multiple independent measurements. The connection remains preliminary and actively debated, but the statistical clustering appears consistently in existing data. In a different context, the structure of quasi-crystals demonstrates the golden ratio operating at the atomic scale. Quasi-crystals are materials that show ordered but non-repeating atomic arrangements. Their diffraction patterns display five-fold symmetry, a geometry that requires the golden ratio to describe. Roger Penrose showed mathematically that the golden ratio is embedded in the foundation of five-fold symmetry. When Dan Shechtman discovered quasi-crystals in the laboratory and received a Nobel Prize for it, he confirmed that the golden ratio was a physical reality at atomic scales, not just a mathematical preference. The golden ratio appears in plant growth, in animal body proportions, in galaxy spiral arms, in quasi-crystal structure, and in patterns within black hole spin and planetary ring spacing. The explanation scientists favor is the same one that applies to Fibonacci spirals. The golden ratio represents an efficient, stable packing configuration. Systems governed by recursive growth or resonance naturally settle into proportions near this value because those proportions minimize interference, maximize stability, and resist perturbation. Physics and biology and mathematics arrive at the same number because it is, in a specific and measurable sense, the least disruptive option. The universe appears to prefer certain numbers, the way water prefers to run downhill. But proportions and spirals are geometry. What happens when the pattern moves deeper into the physics of sound? Because the arrangement of every galaxy you can see tonight traces directly back to sound waves that crossed the early universe before the first star ever lit. In the first 380,000 years of the universe, everything was compressed into a plasma so hot and dense that light could not travel through it. Matter and energy were locked together, vibrating. Pressure waves moved through that plasma the way sound moves through air. These were actual acoustic oscillations, compression and rarefaction spreading outward through the primordial medium at roughly 60% of the speed of light. These waves had a specific size. The distance a wave could travel from its origin point before the universe cooled enough for atoms to form was approximately 490 million light-years. When the plasma cooled and atoms formed, the waves froze. They stopped. The compression pattern they had built was locked into the distribution of matter across space. That frozen pattern is still visible today. It is called baryon acoustic oscillations. Look at the distribution of galaxies across the sky and measure the distances between them statistically. You will find that galaxies are slightly more likely to be separated by distances close to 500 million light-years than by distances slightly larger or smaller. That preferred separation is the echo of those ancient sound waves. The waves compressed matter into shells, and galaxies formed preferentially where the matter was densest, along those shells. The universe's large-scale structure has a subtle preferred scale stamped into it by sound. Cosmologists have used this signature as a standard ruler because the baryon acoustic oscillation scale is known from physics, measuring how large it appears in galaxy surveys at different distances. tells you how fast the universe was expanding at different times in its history. It is one of the most powerful tools available for measuring dark energy, the force driving the universe's accelerating expansion. The precision is remarkable. The signal was predicted theoretically before it was directly detected. When large galaxy surveys confirmed it, the scale matched the prediction within observational error. Sound from the first moments of the universe, frozen into the arrangement of galaxies, confirmed by counting galaxies across billions of light years. This also means that when you look at the night sky, you are seeing an imprint of sound. Every galaxy cluster is partly a product of acoustic physics. The cosmic web is, in part, a score written in the first fraction of a second after the Big Bang, and still readable today. What this demonstrates is that the patterns in the universe are not arbitrary. They carry information about the initial conditions that produced them. They are traces, echoes, residual imprints of physical processes that happened billions of years ago and billions of light years away. The universe is full of fossils. The difference from biological fossils is that these are fossils of physics itself, of processes that determined where matter could gather and where it could not. Every galaxy you can see is where it is partly because of a sound wave. But sound requires a medium to travel through. The medium those Big Bang waves crossed no longer exists in the same form. What replaced it is stranger, a force that is making the universe expand faster and faster, one that seems to grow stronger as space grows larger. And that expansion rate looks like anything but an accident. In 1998, two independent teams of astronomers were measuring how fast the universe expanded at different points in its history. They were studying a specific type of exploding star called a Type Ia supernova, which always explodes with roughly the same brightness. By comparing how bright these supernovas appeared from Earth versus how bright they should be, the astronomers could calculate how far away each one was and how fast the universe had been expanding when that light left it. Both teams expected to find that the expansion was slowing down. Gravity pulls matter together. As the universe aged and spread out, gravity should have been gradually winning, decelerating the expansion. Everyone expected a graph that curved downward. The graph curved upward. The universe was accelerating. Something was driving it apart with increasing force. That something was named dark energy, and it remains one of the deepest unsolved problems in physics. The cosmological constant, which Einstein originally added to his field equations and then removed, calling it his greatest blunder, turned out to be real. It represents a kind of energy density inherent to empty space itself. As the universe expands and creates more space, it creates more of this energy. More energy means more expansion. More expansion means more space. The process feeds itself. The fine-tuning of this constant is extreme. Quantum field theory predicts a value for the energy of empty space that is roughly 10 raised to the power of 120 times larger than what we actually observe. That is a mismatch of incomprehensible size. If the cosmological constant were as large as quantum theory says it should be, the universe would have expanded so violently and so instantly that no structure could have ever formed. Instead, it is precisely small enough that gravity had billions of years to assemble galaxies, stars, and planets before the acceleration became significant. The timing looks calibrated. This is measurable, not impressionistic. Physicists calculate that if dark energy were only slightly larger, galaxies would have been torn apart before stars had time to form inside them. If it were slightly smaller, gravity would have won completely, and the universe would have collapsed long before life could emerge. The value we observe sits in a narrow window between two catastrophes. Some cosmologists call this the coincidence problem. Why does the density of dark energy happen to be comparable to the density of matter right now, at the exact epoch when observers exist to measure it? If dark energy had always dominated, we would not be here. If it had stayed negligible forever, the universe would be collapsing. It becomes significant at just the right error. Several explanations exist. The multiverse solution proposes that observers can only appear in universes where the cosmological constant is compatible with structure. A more speculative idea holds that dark energy is dynamic, changing over time, perhaps tracking the density of matter in ways not yet understood. What is confirmed is that the expansion is real, the acceleration is real, and the value driving it is extraordinary in its precision. And that precision keeps appearing no matter which layer of the universe you examine. Even in the quantum world, where nothing is certain and everything is probable, a pattern persists, a connection between particles that responds across any distance, suggesting the universe's hidden layer is woven together in ways that space and time alone cannot explain. Two particles interact. They become entangled. From that point forward, their quantum states are linked. Measure one particle, and you instantly determine a property of the other, regardless of the distance between them. The two particles could be on opposite sides of the planet, opposite sides of the galaxy, or opposite ends of the observable universe. The correlation is immediate. Einstein called this spooky action at a distance. He found it deeply uncomfortable and spent years trying to prove it did not reflect reality. He believed there had to be hidden variables, some local mechanism that explained the apparent correlation without requiring instant connections across space. In 1964, physicist John Bell developed a mathematical test that could determine whether hidden variables could explain the results or whether entanglement was genuinely non-local. Experiments ran for decades. The results are now definitive. Entanglement is real. Hidden local variables cannot explain it. When physicists perform Bell test experiments, with sufficient precision and enough loopholes closed, the correlations between entangled particles exceed what any local classical mechanism could produce. The universe is, at the quantum level, non-local. Something connects particles across space in a way that does not require traveling through the space between them. This does not mean information travels faster than light. The correlations cannot be used to send a signal because you cannot control what outcome you get when you measure your particle. The result is random. The correlation is real, but unusable for conventional communication. What it does mean is that the universe has a layer of connection that space-time does not fully describe. Physicists use the language of the quantum state. Two entangled particles share a single quantum state, even when separated by vast distances. Measuring one does not send a signal to the other. Instead, the quantum state of the pair collapses simultaneously. The pair was never truly separate in the quantum description, regardless of the physical distance between them. This raises a question about space itself. If two particles can be separated by an enormous distance, yet remain part of a single quantum state, perhaps the classical sense of distance is a derived concept, something that emerges from a deeper layer of reality where everything is already connected. Some physicists take this very seriously. Juan Maldacena and Leonard Susskind proposed what is called the ER equals EPR conjecture. In this framework, a pair of entangled particles is connected by a microscopic wormhole, a shortcut through space-time described by the same mathematics as Einstein-Rosen bridges. Entanglement and geometry may be the same thing described at different levels. If this conjecture is correct, the fabric of space itself may be woven from quantum entanglement. Space would be a structure built on invisible threads connecting quantum states. The non-locality of entanglement would be the foundation the rules are built on, not a strange exception. This remains a theoretical framework, but it is taken seriously by a growing number of physicists working at the intersection of quantum gravity and quantum information. What it points toward is this: the universe has a hidden layer. Visible space with its distances and speed limits may not be the deepest level of reality, Below it sits a structure where connection is the primary fact. That idea has a formal version in physics, and it has a name: the holographic principle. And what it proposes about the nature of three-dimensional space is difficult to accept and harder to dismiss. Imagine every detail of a three-dimensional room encoded on its 2D walls. Every object, every particle, every interaction inside the room is a projection of information stored on the surface surrounding it. The room feels solid, three-dimensional, real, but the fundamental data describing it lives on a flat surface. This is the holographic principle, and it is one of the most seriously studied ideas in modern physics. The principle emerged from a puzzle about black holes. In the 1970s, Stephen Hawking and Jacob Bekenstein worked out the thermodynamics of black holes and discovered something unexpected. The entropy of a black hole, which measures the amount of information it contains, is proportional to the area of its event horizon, not its volume. Every other object in physics stores information proportional to its volume. A box twice as large holds twice as much. A black hole twice as large in area holds twice as much information, even though its volume scales differently. Black holes store information on their surfaces, not in their interiors. In the 1990s, Gerard Hooft and Leonard Susskind generalized this into the holographic principle. They proposed that any region of space contains at most as much information as can be encoded on its boundary surface. The three-dimensional interior of any volume, including the observable universe, might be entirely described by information on a two-dimensional boundary surrounding it. The most concrete mathematical realization of this idea is the anti-de Sitter conformal field theory correspondence, proposed by Juan Maldacena in 1997. This is a precise mathematical duality between a gravitational theory in a three-dimensional space and a quantum field theory on the two-dimensional boundary of that space. The two theories describe different-looking physics, but they are mathematically equivalent. Every calculation you can do in one can be translated exactly into the other. The duality works. Physicists have used it to solve problems in both directions, calculating properties of quantum systems by translating them into gravitational problems where the math is more tractable. Whether it literally means our universe is holographic remains open. The anti-de Sitter space used in Maldacena's duality has a negative cosmological constant, while our universe has a positive one. Extending the principle to a universe like ours is an active area of research. But the core implication is difficult to set aside. If information is more fundamental than space, and if three-dimensional geometry can be fully encoded on a lower dimensional surface, then the space you move through every day may be a kind of emergent structure, a high-level description of something that does not itself have three dimensions at the most basic level. This connects directly back to entanglement. Researchers working on the ER equals EPR framework proposed that three-dimensional space-time geometry emerges from the entanglement structure of quantum states on the boundary. Space is built from quantum information. The pattern repeats itself. The large-scale structure mirrors the human brain. The cosmic web is fractal. The expansion rate is precisely calibrated. Quantum states are non-locally connected, and now three-dimensional space may be information on a surface. And then there is the most direct numerical comparison ever measured between two completely unrelated systems. The density of matter in the cosmic web set against the density of neurons in the human brain. The numbers are closer than they have any right to be. The Vazza-Faletti study touched on this, but the specific numbers deserve their own attention. The human cerebral cortex contains approximately 100 billion neurons. They are distributed across a volume of roughly 1,300 cc's. The cosmic web, mapped across the observable universe, contains on the order of 100 billion galaxies. distributed across a volume of approximately 400 cubic gigaparsecs. The information content of both systems, measured in bits, has been estimated to be of the same order of magnitude, around 10 raised to the power of 27 bits. Two systems with no physical connection, operating at scales roughly 27 orders of magnitude apart, contain comparable amounts of information, by some estimates. That comparison alone is difficult to dismiss. Vasa and Feletti also measured the thickness of the connecting structures in each network. Filaments in the cosmic web range from roughly 1 to 10 million light-years in thickness. Neurons in the brain range from 4 to 100 micrometers in diameter. The ratio of filament thickness to the overall size of each network is comparable across both systems. The fraction of each network occupied by active connecting material, as opposed to empty space, is similar in both cases. In both the brain and the cosmic web, the connecting filaments occupy a small fraction of the total volume, roughly 30%, while the rest is largely empty. These comparisons do not establish a causal connection. Neurons are not galaxies. Dark matter filaments are not axons. The universe did not evolve to be intelligent, and the brain did not form under the influence of gravity alone. Any researcher who suggested a direct causal link would be stepping well outside what the data supports. What the data does support is the conclusion that both systems satisfy similar network constraints. They are both large, complex networks that must distribute energy and information efficiently while remaining structurally stable. Both settled into configurations where a small fraction of the volume does most of the connecting work. Both show similar clustering behaviors when measured with the same statistical tools. This is consistent with the idea that branching and network formation follow universal mathematical rules regardless of the medium. The brain and the cosmic web are two implementations of the same class of mathematical solution, arriving at similar numbers from completely different starting conditions. The density comparisons are striking enough that they have entered scientific literature, not as mystical claims but as quantifiable observations. When two systems at opposite ends of all known scales produce similar density ratios, clustering coefficients, and information content estimates. The most straightforward explanation is a shared mathematical framework. What that framework is remains unclear. Network theory provides partial answers. Statistical physics provides partial answers. Neither fully explains why the universe at its largest scale and the brain at the biological scale converge on such similar organizational numbers. The pattern is confirmed. The explanation is not. And the same mathematical law that might connect them is also connecting earthquake magnitudes to city population sizes, to solar flare intensities, to the distribution of galaxies across the sky. It is one of the most universal laws ever measured, and most people have never encountered it. In any country you choose, the largest city is roughly twice the size of the second largest city, 3 times the size of the third largest, and so on down the list. This holds with surprising precision across dozens of countries and across centuries of urban development. The population of a city at rank n is approximately proportional to 1 divided by n. This is called Zipf's law, and it is a specific example of a power law. Power laws are relationships where one quantity scales as another raised to a fixed exponent. They appear wherever systems grow through preferential attachment, where larger nodes attract more connections than smaller ones simply because they are larger. Cities attract people because they already have people. Wealth accumulates where wealth already exists. But power laws appear in systems that have nothing to do with growth or choice. Earthquakes follow a power law. For every earthquake of a given magnitude, there are roughly 10 times more earthquakes of 1 magnitude smaller. This is called the Gutenberg-Richter law, and it holds across fault systems on every continent. Solar flares follow the same distribution. Small flares happen far more often than large ones, and the relationship between size and frequency follows a power law with a consistent exponent. Word usage in languages follows a power law. The most common word in English appears roughly twice as often as the second most common, 3 times as often as the third. This holds across languages that have never shared a common ancestor. The distribution of galaxies in the cosmic web follows a power law. The sizes of voids follow a power law. The masses of galaxy clusters follow a power law. Power laws arise from a specific type of process called scale invariance. A system is scale invariant when the rules governing its behavior at one scale are the same as the rules at a different scale. There is no characteristic size that defines the system. Earthquakes have no typical magnitude. Cities have no typical mass. Instead, the same proportional relationship holds across the entire range of sizes the system can take. Scale invariance connects directly to fractals. A fractal is scale invariant by definition. The power law distribution is the statistical signature of fractal geometry. When you measure the power law exponent for the cosmic web, you are measuring the same thing as its fractal dimension, just approached from a different angle. What makes power laws deeply significant is that they are process signatures. Finding a power law in a data set tells you something about how the system formed. It means the system grew through a process where size begat size, where existing structure attracted new structure, where no single scale dominated. The universe, at every level where power laws appear, grew through preferential attachment, through the simple rule that what is big gets bigger. That rule is not complicated, but applied at every scale simultaneously, from quantum fluctuations to galaxy superclusters, it produces a universe with the same mathematical fingerprint, from the smallest measurable structure to the largest. And embedded in that fingerprint, woven through the mathematics of power laws and fractals and cosmic structure, is a number you have encountered since grade school, one that has no business appearing inside a quantum wave equation, and yet it is there every time you look. Pi is approximately 3.14159. Most people learn it as the ratio of a circle's circumference to its diameter. Every calculation involving a curved path, a rotation, or a wave brings pi into the picture. So it makes sense that pi appears in physics. Waves are circular, orbits are circular, fields spread outward from a source in spherical shells. Of course pi shows up, but then you look more carefully and pi begins appearing in places where circles are nowhere in sight. The Gaussian distribution, the bell curve that describes random variation in everything from human heights to measurement errors, contains pi in its formula. The bell curve is not a circle. It does not involve rotation or circumference, yet pi sits inside the normalization factor that makes the equation work. Remove pi and the probabilities no longer add up to 1. Pi is structurally necessary. Stirling's approximation, which estimates the factorial of large numbers, contains pi. Factorials are about counting arrangements, combinations of objects and sequences. No geometry involved. Yet pi appears. The formula for total radiation emitted by a perfect black body, the Stefan-Boltzmann law, contains pi to the 4th power. Black body radiation is about how hot objects emit energy across a spectrum. Pi is embedded in the answer because of how quantum states distribute themselves across energy levels, a distribution that involves summing over all possible frequencies. The math forces pi in through the shape of an infinite sum, not through any physical circle. Einstein's field equations contain pi in the constant linking the geometry of space to the energy and momentum, causing that geometry. The constant is 8 pi divided by the speed of light to the 4th power, multiplied by Newton's gravitational constant. Why 8 pi? The factor emerges from the mathematical structure of how three-dimensional space integrates over a spherical volume in the context of a tensor field equation. Pi is built into the geometry of integration in higher dimensional calculus. Quantum mechanics uses pi in the Heisenberg uncertainty principle. The principle states that the uncertainty in position multiplied by the uncertainty in momentum is always greater than or equal to a constant, divided by 4 pi. That 4 pi comes from the mathematics of wave functions in Fourier space, where waves and their frequency representations are connected through pi in the fundamental transform equations. In all of these cases, pi is not inserted as a convenience. It is demanded by the mathematics. The equations will not balance without it. This means pi is not simply the number that describes circles. Pi is a structural constant of mathematics itself, woven into the fabric of how continuous quantities relate to each other across any domain involving smoothness, spread, or oscillation. Physics is full of smooth fields, spreading waves, and oscillating quantities. Pi follows wherever those things go. The universe runs on pi the way a machine runs on oil. It is everywhere the parts touch. And somewhere in the oldest light in the universe, there is a direction, a preferred axis, a feature that should not exist in a cosmos that looks the same from every angle, an anomaly so persistent and so strange that scientists named it the axis of evil, and it has refused to disappear for over 2 decades. The universe, according to the standard model of cosmology, has no preferred direction. Stand anywhere inside it, point anywhere, and the large-scale structure should look statistically identical. This principle is called isotropy, and it is one of the foundational assumptions underlying nearly all of modern cosmology. The cosmic microwave background appears to confirm this. In every direction you look, the temperature is almost the same. The tiny variations that exist are consistent with a random distribution of quantum fluctuations from the early universe. No direction should stand out, except one does. When the Wilkinson Microwave Anisotropy Probe mapped the cosmic microwave background in 2003, physicists noticed something they had not expected. The largest scale features of the temperature map, called the quadrupole and octupole moments, were aligned with each other. They pointed in the same direction across the sky. That alignment was far stronger than random fluctuations should produce. The direction they pointed toward happened to be the same direction as the ecliptic, the plane of Earth's orbit around the Sun. It was also correlated with the equinoxes. The largest pattern in the deepest map of the universe was pointing toward a feature of our local solar system, a cosmic signal encoded across the entire observable universe, lined up with the geometry of our tiny corner of it. This is a confirmed observational feature. When the Planck satellite remapped the cosmic microwave background with much higher resolution a decade later, the alignment was still there. It had not washed out. It had not been explained as instrumental error. It was real. Cosmologists named it the axis of evil, borrowing the term partly as dark humor because the alignment violated their expectations so thoroughly. Several explanations have been proposed. Some researchers argue it is a statistical fluke. The quadrupole and octupole are the largest and therefore rarest patterns in the cosmic microwave background, meaning the sample size for comparing them is inherently tiny. With only one universe to observe, a coincidental alignment cannot be rigorously ruled out. Others propose foreground contamination. Local structures like the Milky Way or nearby galaxy clusters might be imprinting their geometry onto the measurement in ways that are difficult to fully subtract. If some local emission creates a faint directional bias, it could mimic an intrinsic cosmic alignment. A third class of explanations is more radical. If the universe has a non-trivial topology, meaning it wraps around itself in a specific way, different directions in space would not be equivalent. The universe might have a preferred axis built into its global geometry that we have not yet mapped completely. Some versions of inflation predict a universe that is not perfectly isotropic, where initial conditions created a slight directional bias that persisted and is detectable today. None of these explanations is confirmed. The axis of evil remains an open anomaly. What makes it genuinely unsettling is its scale. The pattern exists at the largest measurable scale of the universe. If the largest scale structure has a preferred direction, the implications for the standard model are significant. The foundational assumption of isotropy may need revision. Revision at that level does not produce small changes. A universe with a preferred direction would mean our maps of cosmic evolution, our calculations of dark energy, our understanding of the Big Bang itself, all built on the assumption of isotropy, would need to be reconsidered. The anomaly is confirmed, the explanation remains a mystery. And what comes after is stranger still, because the same kind of repeating cellular pattern that organizes the cosmic web also structures the wings of a dragonfly and the spots on a giraffe. And no one has fully explained why the geometry of living skin and the geometry of galaxy boundaries should share the same underlying template. A dragonfly wing is not solid. Under magnification, it reveals a network of interconnected cells, irregular polygons packed tightly together, sharing thin borders, enclosing empty chambers. The pattern is called a Voronoi tessellation. It divides a surface into cells based on proximity to a set of seed points, with each cell containing all the space closer to its seed than to any other. A giraffe's coat follows the same geometry. So does a foam of soap bubbles. So does the surface of a dried mudflat, cracking under heat. So does the distribution of superclusters across the observable universe. Voronoi geometry appears wherever a surface or volume is divided by competing local centers. Each center claims the territory closest to it, and the result is a partition of space into irregular but tightly packed cells with shared boundaries. In biology, this pattern arises through competition. Cells in a developing embryo grow outward from their nuclei until they meet neighboring cells. They stop at the border. The result is a Voronoi tessellation of tissue. In a dragonfly wing, this cellular structure provides maximum stiffness per unit of material, a solution that natural selection landed on because it is mechanically efficient. In a giraffe's skin, the pattern distributes melanin-producing cells with minimal overlap and maximal coverage. The cosmic web produces the same geometry through an entirely different process. In the early universe, matter was distributed nearly uniformly with tiny overdense regions scattered through it. Gravity pulled surrounding matter toward those overdense regions, emptying the space between them. As matter drained away, the regions between clusters became voids. The boundaries where material from adjacent clusters met formed the walls and filaments of the cosmic web. Each galaxy cluster sits inside its own gravitational territory, claiming the matter nearest to it, sharing boundaries with adjacent clusters. The process is gravitational, not biological. The mathematics describing it is Voronoi geometry. Researchers have used Voronoi tessellations to model the cosmic web and found that the model reproduces the observed galaxy distribution with high accuracy. The sizes and shapes of cosmic voids follow the same statistical distributions as cells in a biological tissue under specific growth conditions. The boundary thickness between adjacent cosmic regions mirrors the boundary thickness between cells in a foam relative to the overall scale of each system. This is measurable. The statistics of cell sizes, the angles at which boundaries meet, the distribution of the number of neighbors each cell shares, all of these are quantifiable. When cosmologists apply them to the large-scale structure of the universe, and biologists apply them to tissue architecture, the distributions overlap. Voronoi geometry is the fingerprint of any process where competing centers divide space. The fact that gravity and cell growth both produce it means the geometry is not caused by either process specifically. It is caused by the mathematical structure of spatial competition itself. The universe and a dragonfly wing both contain the same solution to the problem of dividing space efficiently. They arrived at it through completely different physics, separated by a scale difference that spans roughly 40 orders of magnitude. That same tendency to collapse into efficient geometry goes back even further. In the earliest moments after the Big Bang, before galaxies, before stars, before any structure existed at all, matter was already falling into a shape. A flat, pancake-like shape, and the mathematician who predicted it did so decades before anyone could confirm it. In 1970, a Soviet mathematician named Yakov Zeldovich made a prediction that most of his contemporaries found difficult to visualize. He argued that the first large structures to form in the universe would be flat. Matter would not collapse evenly in all directions, simultaneously. It would collapse fastest along one axis, forming thin sheets before any filaments or clusters appeared. He called these sheets pancakes. The prediction was based on pure mathematics, applied to the dynamics of a slightly uneven distribution of matter under gravity. It required no observations, no experiments, just the equations of gravitational collapse applied to realistic initial conditions. Decades later, when three-dimensional surveys of galaxy positions became possible, what astronomers found matched Zeldovich's prediction. The large-scale structure of the universe is organized into sheets, walls of galaxies spanning hundreds of millions of light-years, with vast empty voids on either side. Filaments connect where sheets intersect. Clusters form where filaments meet. The hierarchy goes flat sheet, then filament, then cluster. The order Zeldovich predicted from his desk. The mathematics behind this collapse is elegant. In a uniform gas collapsing under gravity, any small initial overdensity will grow. But overdensities are not spherical. The real distribution of matter in the early universe had fluctuations of different sizes and shapes in three-dimensional space. The direction in which each fluctuation was smallest would collapse first, because gravity had the shortest distance to pull matter across. The result was preferential collapse along one dimension before the other two caught up. A three-dimensional cloud became a sheet. Then the sheet collapsed along its second dimension into a filament. Then the filament along its third into a cluster. The structure built itself in stages, each stage creating the geometry for the next. What makes this deeply satisfying is that the prediction came from mathematics alone, without reference to any specific physical observation. Zeldovich wrote equations describing how gravity acts on a density field, then asked what shapes those equations inevitably produce. The answer was sheets. When the universe was finally mapped in 3 dimensions, the sheets were there. This is one of the clearest examples in cosmology of mathematical prediction preceding observation. The structure existed before anyone looked. The math described it in advance. The Zeldovich pancake is now confirmed as the first stage of what is called hierarchical structure formation. Small structures collapsed first and merged into larger ones. Pancakes became the raw material for filaments. Filaments fed clusters. Clusters fed superclusters. The universe built its complexity from the bottom up, one gravitational stage at a time. But gravity alone cannot explain everything. At every step of this process, a fundamental limit was operating. A limit on how small and how fast any pattern can get before the universe itself refuses to let the pattern continue. That limit is not a wall built from matter or energy. It is built from something far more fundamental, a constant woven into the structure of space and time. And the physicist who first measured it had no idea he had found the floor of reality. In 1900, Max Planck was trying to solve a specific embarrassment in physics. The equations describing how hot objects emit radiation predicted that an object should emit infinite energy at short wavelengths. Every warm object in the universe should instantly radiate away all its energy in a catastrophic burst of high-frequency light. The universe should be cold and dark. Planck fixed the equations by introducing a small constant, a minimum packet of energy that could be exchanged during any interaction. He called it a quantum of action, and he labeled it with the letter H. He described it later as a desperate mathematical rescue, a fix he expected would eventually be replaced by a more satisfying explanation. It never was. The constant held. It deepened. It became the foundation of quantum mechanics. Planck's constant has a value of approximately 6.626 times 10 to the negative 34th joule seconds. That number is extraordinarily small. It means that on the scales of ordinary human experience, the quantum graininess of reality is completely invisible. A baseball, a planet, a galaxy, all of these operate at energy scales so far above Planck's constant that quantum effects wash out entirely. But at the scale of atoms and below, that constant is everything. It sets the minimum amount of energy a system can exchange. It determines the minimum uncertainty in any measurement of position and momentum. It establishes the scale at which the smooth, continuous behavior of large objects breaks down into discrete, probabilistic behavior. Below its threshold, space and time themselves lose their familiar meaning. The Planck length, derived from Planck's constant combined with the speed of light and the gravitational constant, is approximately 1.6 times 10 to the negative 35th meters. That is roughly 10 to the 20th times smaller than a proton. At scales smaller than the Planck length, the geometry of space-time itself becomes uncertain. The smooth fabric of space breaks into a quantum foam where the concepts of distance and duration become meaningless in their classical sense. This is a hard limit on the pattern. Every fractal structure in the universe, every branching filament, every repeating geometry hits this flaw. The pattern cannot go smaller than Planck's constant allows. Reality has a minimum pixel size. What is strange is that this constant appears to be an intrinsic feature of nature, not a consequence of any other law. Physicists cannot derive Planck's constant from a deeper principle. It is measured, accepted, and built upon. Its origin is unknown. The same situation applies to the speed of light and the gravitational constant. The three together define the Planck scale, the boundary at which all known physics dissolves into a regime where no current theory works. String theory, loop quantum gravity, and other frameworks are all attempts to describe what happens there. None has succeeded completely. The Planck scale is the bottom of the pattern. The cosmic web is the top. Between them spans the entirety of known physical reality, and across that entire span the same mathematical structures keep repeating, which forces a question that physicists have debated since at least the time of Galileo, and which is becoming harder to defer. Why does mathematics describe all of this so perfectly? Why does a set of human symbols and rules, invented to count sheep and measure land, reach all the way to the floor and ceiling of reality without breaking? In 1960, the physicist Eugene Wigner published an essay titled "The Unreasonable Effectiveness of Mathematics in the Natural Sciences." The title itself captures the problem. Mathematics works too well. It is not just useful for physics, it is unnervingly precise, producing predictions confirmed to 15 decimal places, describing phenomena that existed billions of years before humans arrived to name them. Wigner found this troubling. He had no satisfying explanation, and said so directly. The puzzle starts with what mathematics is. Most mathematicians discover their results, rather than invent them. When a mathematician proves a theorem, the result feels like something uncovered, not something constructed. Prime numbers do not behave the way they do because mathematicians decided they should. The properties of prime numbers were always what they are. Mathematicians found them. This is called mathematical Platonism, the view that mathematical objects exist independently of human minds in some abstract realm, where they simply are. Plato held this view roughly 2,400 years ago. Many working mathematicians hold it today, not as philosophy, but as a practical intuition that matches their experience. If mathematics exists independently of humans, then the universe using it makes sense. The universe was built from abstract structures that were already real before any mind arrived to study them. But if mathematics is a human invention, a language developed to organize observations, then its effectiveness at describing the deep structure of nature is genuinely mysterious. Why would a tool invented for counting and measuring turn out to reach all the way to the geometry of space-time and the behavior of subatomic particles? Complex numbers are a vivid example. They were invented in the 16th century to solve equations that seemed to have no real solutions. Mathematicians created imaginary numbers purely to make the algebra work. 2 centuries later, quantum mechanics turned out to require complex numbers at its foundation. The wave function, the central object of quantum theory, is complex valued. Remove the complex numbers, and the theory does not function. The mathematics created for pure abstract reasons became physically necessary. The same story repeated with non-Euclidean geometry. Mathematicians in the 19th century explored what geometry would look like if the parallel postulate were dropped. They developed curved geometries with no reference to any physical observation. Decades later, Einstein's general relativity required precisely those curved geometries to describe spacetime. The mathematicians had mapped the territory before anyone knew the territory existed. 3 explanations compete. The first is that physics selects for mathematics that works, and over centuries, only the mathematics that describe nature survived in the curriculum. We learned curved geometry because curved geometry matters. The rest fell away. The second is that the universe is mathematical at its foundation. Physical objects are mathematical objects. The universe follows mathematical laws because the universe is made of mathematics. The third is that human cognition evolved in a physical universe and therefore reflects its structure. The mathematics we find natural is natural because it mirrors the reality we evolved inside. We are not discovering external patterns. We are recognizing our own reflection. None of these 3 answers is satisfying without remainder. Each leaves something unexplained. What is undeniable is that the precision is real. And underneath the mathematics, there may be additional structure we have not yet uncovered. Structure that would explain where the patterns come from. Structure that some physicists argue is hiding in dimensions we cannot see. The standard model of particle physics describes every known particle and every known force except gravity, using a framework built on quantum field theory. It is extraordinarily precise. It has correctly predicted the magnetic moment of the electron to more than 10 decimal places. It is one of the most tested theories in the history of science. It also has serious problems. It does not include gravity. It contains around 20 free parameters, numbers that must be measured rather than derived. It offers no explanation for why particles have the masses they have. And it describes a universe where most of the matter and energy appears to be missing. The dark matter and dark energy that dominate the cosmos but fit nowhere in the model. String theory is the most developed attempt to solve these problems simultaneously. The core idea is this: replace every point particle in the standard model with a tiny one-dimensional string. Different vibration modes of the string produce different particles. The electron is a string vibrating one way. The photon is a string vibrating another way. Gravity emerges naturally from one specific string vibration mode, unlike in the standard model where gravity must be awkwardly excluded. For string theory to be mathematically consistent, space must have more than the 3 spatial dimensions. We experience the original formulations required 25 spatial dimensions. Modern superstring theory requires 9 spatial dimensions, 10 counting time. The 6 or 7 extra spatial dimensions we do not observe are curled up at scales close to the Planck length, so small that no current experiment can directly detect them. The shape of these hidden dimensions determines everything. The way extra dimensions are compactified, folded up and tucked away, sets the values of the fundamental constants. A different folding produces a different electron mass, a different strength of gravity, a different cosmological constant. The landscape of possible compactifications is estimated to contain something like 10 raised to the power of 500 distinct configurations, each producing a universe with different physical laws. This is called the string landscape, and it has profound implications. If each compactification corresponds to a real universe, then the specific set of physical constants we observe reflects one particular folded geometry among an enormous number of possibilities. The patterns we see in our universe, the branching structures, the fractal geometry, the precisely tuned constants, all of them would be consequences of the specific way the hidden dimensions are folded in our configuration. The spiral of a galaxy and the arrangement of the cosmic web would trace back to geometry at a scale 10 to the 35th times smaller than a proton. String theory has not been experimentally confirmed. Its extra dimensions have not been detected. The string landscape raises the uncomfortable possibility that the theory cannot make unique predictions because any observation is consistent with some configuration among 10 to the 500 options. Critics argue this makes it untestable in principle. Supporters argue that testability will come as instruments improve and that the mathematical consistency of the framework is itself significant evidence. A theory that ties together gravity, quantum mechanics, and all known particles in a single coherent structure without logical contradiction is not easily dismissed. What makes string theory relevant to the hidden pattern is its central claim. The visible regularities of the universe may be projections of an invisible geometry. The pattern is not just on the surface, it goes all the way down into dimensions too small for any current instrument to reach. But you do not need hidden dimensions to find something inexplicable. Sometimes you just need to look at how galaxies spin, because every galaxy spins in a way that breaks the laws of physics as currently written. When you spin a ball of clay on a wheel, the outer edges rotate slower than the center. This is what physics predicts for any rotating disk of matter, and it matches perfectly for the planets of the solar system. Mercury, closest to the Sun, completes an orbit in 88 days. Neptune, far out in the cold, takes 165 years. Speed drops with distance from the center, exactly as Newton's gravity demands. Galaxies should behave the same way. In the 1970s, astronomer Vera Rubin and her colleagues mapped the rotation speeds of stars at different distances from the centers of dozens of spiral galaxies. Stars near the center of each galaxy moved fast. Moving outward, the speed should have dropped. Instead, it stayed roughly constant all the way to the outermost visible edge of each galaxy. The rotation curves were flat. Flat rotation curves mean that stars far from the galactic center are moving faster than the visible mass of the galaxy can explain. If you calculate how much mass would be needed to keep those outer stars in orbit at their observed speeds, you get a number far larger than the mass of all the visible stars, gas, and dust combined. Something invisible is supplying enormous additional gravity. This is one of the original pieces of evidence for dark matter, the invisible mass that keeps galaxies rotating too fast. But the pattern has an additional layer of strangeness that goes beyond simply invoking dark matter. The rotation curves of galaxies are almost identical in shape, regardless of galaxy size, brightness, age, or composition. A small dwarf galaxy and a massive spiral galaxy show flat rotation curves with the same general profile. The specific speed at which they flatten depends on the galaxy's mass, but the shape of the curve, flat and extended, is universal. This universality is difficult to explain with dark matter alone. If dark matter is a separate component, distributed around each galaxy in a halo, the shape of the rotation curve would depend on how the dark matter halo is distributed. which should vary from galaxy to galaxy based on each galaxy's formation history. The remarkable similarity across wildly different galaxies suggests some deeper physical principle is at work. One alternative framework, called modified Newtonian dynamics, proposes that gravity behaves differently at very low accelerations than Newton's law predicts. In this framework, no dark matter is needed. The same modification of gravity applied to any galaxy, regardless of mass, automatically produces a flat rotation curve. The theory matches observed rotation curves across a wide range of galaxies with a single adjustable parameter. Neither dark matter nor modified Newtonian dynamics fully explains all observations simultaneously. Certain galaxy clusters are better explained by dark matter. Certain individual galaxy rotation curves are better explained by modified Newtonian dynamics. No single framework has won the debate. What remains confirmed and unexplained is the universality itself. Galaxies separated by billions of light years, formed at different times with different masses and compositions, all rotate with the same characteristic flat profile. Whatever the explanation, it must apply universally across all scales and all ages of galactic history. The pattern in galaxy rotation is another expression of the same underlying universality, and it has a direct numerical connection to the quantum fluctuations predicted at the very beginning of time, a connection so precise it borders on uncomfortable. The cosmic microwave background is covered in Chapter 7 in broad strokes. But the precision of the quantum-to-cosmic connection deserves its own examination because the numbers involved are almost absurd in their accuracy. Cosmic inflation happened in the first tiny fraction of a second after the Big Bang. During inflation, the universe expanded from a size smaller than an atom to the size of a grapefruit in a time so short it cannot be expressed in ordinary language. During that expansion, quantum fluctuations, random variations in the density of the energy field driving inflation, were stretched to macroscopic scales. Regions that differed by a quantum whisper became regions that differed by measurable fractions of temperature. Those temperature differences across the cosmic microwave background are the direct, stretched imprints of quantum randomness from the moment of creation. Quantum mechanics makes specific predictions about those fluctuations. The power spectrum of the cosmic microwave background, which describes how much variation exists at each angular scale across the sky, is predicted by inflationary quantum mechanics to follow a nearly scale-invariant distribution, meaning roughly equal amounts of variation at every scale with a slight tilt toward more variation at larger scales. The prediction is called the Harrison-Zeldovich spectrum, and when it was first proposed in the early 1970s, the cosmic microwave background had barely been discovered. No satellite had mapped it in detail. The prediction was theoretical. When the Wilkinson Microwave Anisotropy Probe delivered its first full sky map in 2003, the measured power spectrum matched the Harrison-Zeldovich prediction across every angular scale the instrument could resolve. When the Planck satellite improved on those measurements a decade later, with higher resolution and sensitivity, the match held, tightened, and revealed the predicted slight tilt with high statistical confidence. The spectral tilt, called the scalar spectral index, was measured at approximately 0.968. Inflationary models had predicted a value slightly less than 1, with many models clustering around 0.9 second. A prediction made on theoretical grounds, derived from quantum mechanics applied to a hypothetical burst of expansion, matched a measurement made by a satellite staring at the oldest light in the universe, accurate to 2 decimal places. This is one of the most precise confirmations of any cosmological theory ever achieved. It connects the physics of the smallest possible scales, quantum fields in the first moments of time, directly to the largest possible structures, the temperature pattern of the entire observable universe. The connection is not metaphorical. It is quantitative. Quantum uncertainty from the birth of the universe is written in the temperature of the sky, and the formula predicting that temperature was derived before anyone measured it. What this tells you is that the patterns are not accidents of large-scale physics. They were seeded by physics at the very bottom of the scale hierarchy, imprinted from the quantum realm upward through every size of structure between atoms and superclusters. Quantum mechanics did not just influence the early universe, it authored the architecture that all subsequent pattern making was built on. And the bridge between quantum randomness and cosmic order has a name. A single concept that explains how blind, simple rules applied at small scales produce breathtaking complexity at large ones. The concept is emergence, and it is the secret engine driving everything. A single ant is not intelligent. It follows a small set of chemical rules. If it smells a pheromone trail, it follows it and reinforces it. If it finds food, it returns to the nest while releasing pheromones. No ant understands the colony. No ant plans the architecture of the tunnels or the division of labor. Each ant follows its rules locally, blind to the global result. The colony is organized, adaptive, and structurally sophisticated. This is emergence. Complex, organized behavior arising from simple rules followed at a smaller scale, with no central planner, no blueprint, no awareness of the larger pattern. Emergence appears throughout nature at every scale. Water molecules each follow the physics of hydrogen bonding. Their collective behavior produces surface tension, capillary action, and the specific properties of liquid water, properties that no single molecule possesses. Individual neurons fire or do not fire based on local electrochemical signals. Their collective activity produces thought, memory, and consciousness, none of which exist in any single neuron. The universe uses emergence at every level of its structure. In the cosmic web, each particle of dark matter responds only to local gravity. No particle knows it is part of a filament. No galaxy knows it is part of a supercluster. Each simply responds to the mass nearest to it. The result, after billions of years of local interaction, is the enormous, branching cellular structure that spans the observable universe. The pattern is not programmed from the top. It builds from the bottom. Physicists call this bottom-up structure formation, and its mathematics is understood well enough to simulate. Cosmological simulations like the Millennium Simulation and the illustrious TNG project start with a nearly uniform distribution of particles and apply only the known laws of gravity, hydrodynamics, and particle physics. No extra instructions are given, no target structure is specified. The simulations produce a cosmic web that matches the observed universe in its statistical properties, its void sizes, its filament thicknesses, its galaxy clustering patterns. Simple local rules applied to billions of particles for billions of simulated years generate the structure we actually observe. This confirms that the pattern does not require an external architect. The rules themselves, applied locally and consistently, inevitably produce the global structure. The universe is self-organizing in the deepest sense. But emergence does not explain everything. The rules themselves must come from somewhere. Gravity has the specific strength it has. Quantum fluctuations have the specific spectrum they have. The initial conditions were what they were. Emergence explains how the patterns build upward from rules. It does not explain why the rules are what they are, or why those particular rules produce organized complexity rather than featureless chaos. The most unsettling version of the emergence problem comes from the Mandelbrot set. This is a mathematical object defined by an almost childishly simple rule, applied over and over to complex numbers. The result is infinite complexity. Zoom into the Mandelbrot set at any scale, and new structures appear. Spirals, filaments, bulbs, miniature copies of the whole shape at every depth of magnification. The rule is simple, the structure is inexhaustible, and the distribution of galaxy voids across the observable universe follows the same kind of self-similar geometry that the Mandelbrot set makes visible. A mathematical object defined by a rule. A universe defined by physics, both producing the same class of infinite, self-similar pattern. The Mandelbrot set is generated by a single equation applied repeatedly. Take a complex number, square it, add the original number back, and repeat. Some starting points spiral outward to infinity. Others stay bounded forever, cycling near zero. The boundary between those two behaviors, the edge of the Mandelbrot set, is where the interesting structure lives. That boundary is infinitely complex. Zoom in anywhere along it, and new spirals appear. New miniature copies of the whole shape emerge from the detail. There is no scale at which the edge becomes simple or smooth. The complexity is genuinely infinite, produced by one line of mathematics applied over and over. The distribution of voids in the cosmic web shows the same class of structure. Cosmic voids are the enormous empty regions between galaxy filaments and walls. They range from small underdensities spanning tens of millions of light-years to the largest known voids spanning several 100 million light-years. Voids are not evenly distributed. They cluster. Large voids contain smaller subvoids. The boundaries between adjacent voids are filaments and sheets of galaxies. When astronomers map void sizes statistically, the distribution follows a self-similar pattern. The number of voids of a given size scales with size according to a power law. Large voids are rarer than small voids in a specific proportional relationship that holds across a wide range of scales. The same mathematical signature appears at different zoom levels. This is a measurable fractal property of empty space itself. The connection to the Mandelbrot set is structural, not literal. Galaxy voids are not complex numbers. Gravity is not the squaring function, but both systems produce self-similar structure from iterative processes. The Mandelbrot set applies one mathematical operation repeatedly to numbers. The cosmic web applies one physical law, gravity, repeatedly to matter. Both produce structures that look similar at different scales. The mathematician John Barrow wrote that the universe has the character of a mathematical object. Not that the universe resembles mathematics in a loose way, but that its structural properties have the precise character of objects that exist in mathematical space. The void distribution of the cosmic web fits this description. Its power law scaling is not an approximation. It is a precise mathematical signature. Within the void hierarchy, structures called supervoids and great voids represent the largest underdense regions in the known universe. The Boots void spans roughly 330 million light-years and contains almost no galaxies. Physicists are still debating whether its emptiness can be fully explained by standard structure formation models. Some analyses suggest supervoids are slightly more common than the standard model predicts, which could indicate that dark energy is slightly stronger than measured, or that some additional mechanism is evacuating matter from void interiors. The self-similar structure of voids gives cosmologists a tool because the scaling follows a power law. Measuring voids at different cosmic epochs tracks how structure evolved over time. Voids grow as dark energy pushes matter outward, and the rate of growth constrains the properties of dark energy. Empty space is not featureless. It has architecture. The pattern fills even the absence of galaxies with mathematical structure. And when you scale back up from individual voids to the full picture of how galaxies are arranged throughout the universe, what you find is a structure so regular, so geometric, so systematically repeated at every scale, that the first astronomers to map it simply could not believe what they were seeing. In 1989, Margaret Geller and John Huchra at the Harvard-Smithsonian Center for Astrophysics released a map of galaxy positions drawn from a systematic survey of a strip of the sky. The image showed something that stopped the astronomical community. Galaxies were arranged in thin, curved arcs. Empty bubbles sat between the arcs, each bubble hundreds of millions of light-years across. Where arcs intersected, clusters of galaxies were packed tightly together. The overall impression was of a foam, a three-dimensional cellular structure of interlocking shells. Geller's description of what she saw became famous. She said it looked like the surface of a sponge, or the pattern of soap bubbles, a structure that nobody had predicted in that detail, and which required a complete rethinking of how matter distributed itself over cosmic time. The discovery was called the Great Wall, a sheet of galaxies spanning 500 million light-years. At the time, it was the largest known structure in the universe. It has since been surpassed by the Sloan Great Wall and the Hercules Corona Borealis Great Wall, which spans approximately 10 billion light-years and remains the largest confirmed cosmic structure known. That last one is worth pausing on. 10 billion light-years. The observable universe is about 93 billion light-years across in total diameter. One single coherent structure spans more than 10% of the observable universe. The cellular pattern Geller and Hutra mapped in 1989 has been confirmed and extended by every subsequent survey. The 2-degree field galaxy redshift survey, the Sloan Digital Sky Survey, and the Dark Energy Spectroscopic Instrument Survey have each added depth and resolution to the picture. The conclusion from all of them is the same. Galaxies are not randomly scattered. They trace a cellular structure of walls, filaments, nodes, and voids that repeats at multiple scales. The cell sizes are not identical. Some cells are smaller, some larger. But the pattern of cells itself persists. Zoom in on a section of the cosmic map and you see cells. Zoom out and you see the same cells, just smaller relative to your field of view. Zoom further out to the very largest scales and the cells begin to become individually unresolvable, blending into a rough statistical uniformity. This is the boundary of the fractal behavior identified in Chapter 6. The cellular pattern is self-similar up to scales of roughly 300 million light-years. Beyond that scale, the universe approaches the smooth uniformity predicted by the cosmological principle. The cellular structure confirmed what simulations predicted. Gravity acting on quantum fluctuations produces cells. The sizes and shapes of those cells encode information about the initial fluctuations, the properties of dark matter, and the history of cosmic expansion. Reading the cells correctly gives cosmologists a three-dimensional record of cosmic history. What the maps also revealed, and what no simulation fully anticipated, is the degree of alignment within this structure. Filaments point in preferred directions. Voids line up. Spin axes of galaxies within the same filament point the same way. And that last observation, the alignment of galaxy spins across distances far too great for any known force to coordinate, is one of the most unsettling patterns in all of contemporary astrophysics. Galaxies spin, each one rotates around its own center, with stars and gas orbiting the galactic core over timescales of hundreds of millions of years. The direction each galaxy spins, its angular momentum, is determined by the conditions of its formation. As a protogalactic cloud collapsed under gravity, any slight initial rotation was amplified as the cloud contracted, the same way a spinning figure skater speeds up by pulling in their arms. Because the initial rotation of each protogalactic cloud should have been set by local conditions, independent of what was happening far away, the spin axes of galaxies should be randomly oriented across the sky. Look at 1,000 galaxies in all directions, and they should spin in all directions, with no preferred pattern. Multiple surveys have found this assumption is wrong. Studies of galaxy spin orientations across the Sloan Digital Sky Survey data found that galaxies within the same cosmic filament tend to spin with their axes aligned parallel to the filament direction. Other analyses found alignment perpendicular to filament boundaries. The results vary somewhat by filament type and galaxy mass, but consistent alignment signals have been measured in data sets covering hundreds of millions of light years. A 2019 analysis of radio galaxy spin vectors found a correlation in spin direction across a region spanning roughly 3 billion light years. This is a scale so large that no known physical mechanism has time to communicate across it. Light itself would need 3 billion years to cross that distance. For a force to align galaxy spins across such a scale, it would have had to act during the very earliest phases of the universe, before galaxies existed. The most widely discussed explanation involves the filaments of the cosmic web itself. As matter falls into filaments during structure formation, it carries angular momentum that reflects the large-scale geometry of the surrounding matter distribution. Filaments impose a preferred direction on the infall of gas and dark matter. Galaxies forming within that filament inherit a bias in their angular momentum direction. The alignment is built in from the beginning, seeded by the large-scale structure that formed before any individual galaxy existed. This explanation is theoretically reasonable. Simulations reproduce weak alignment signals consistent with this mechanism. But the observational signals in some datasets appear stronger than simulations predict, which means either the mechanism is not fully captured in current models, or additional physics is contributing. A smaller group of researchers has explored whether the alignment could reflect primordial magnetic fields from the early universe, large-scale velocity flows that persist from the first moments of structure formation, or topological features of the universe's geometry. None of these alternatives has gathered strong observational support. What is confirmed is the alignment. Galaxies separated by distances that dwarf any known physical interaction share a statistical preference in their spin directions. The structure of space, inherited from the earliest phases of cosmic evolution, encoded angular momentum preferences across scales that still manifest today in which way galaxies rotate. The universe coordinates its structure across distances that should prevent coordination. And if the spin of matter reflects something embedded in the geometry of the cosmos from the very beginning, then the question of what governs that geometry leads directly to the deepest organizing principle ever discovered in physics. A principle so fundamental that every force, every particle, and every pattern in this script ultimately traces back to it. In 1915, a mathematician named Emmy Noether proved one of the most consequential theorems in the history of physics. She showed that every continuous symmetry in the laws of physics corresponds to a conserved quantity. The connection is precise and general. Symmetry produces conservation, always without exception. If the laws of physics are the same today as they were yesterday, energy is conserved. If the laws of physics work the same way here as they do a mile to the left, momentum is conserved. If the laws of physics look the same after rotating your coordinate system, angular momentum is conserved. Conservation of energy, momentum, and angular momentum, three of the most fundamental principles in all of science, are consequences of three symmetries. Noether's theorem does not stop there. Electromagnetism arises from a symmetry called local gauge invariance. If you are free to change the mathematical phase of the electromagnetic field independently at every point in space, without affecting any observable measurement, then the laws of electromagnetism must exist to enforce consistency. Electromagnetism is the price the universe pays for that symmetry. The weak nuclear force arises from a different gauge symmetry. The strong nuclear force arises from yet another. The standard model of particle physics is essentially a catalogue of symmetries and the forces they require. Every known force is the consequence of a specific mathematical symmetry imposed on the laws of physics. Gravity is described by general relativity, which is built on the symmetry of general covariance. The laws of physics must take the same form in any coordinate system, accelerating or not. Einstein derived his field equations by demanding that this symmetry hold. Gravity is what general covariance demands. The patterns seen across the universe, from the fractal branching of the cosmic web to the golden ratio spirals of galaxies to the alignment of galaxy spins, are all downstream consequences of the symmetries that govern the forces that produce them. But symmetry is not just a tool for deriving forces. It is a filtering mechanism. Among all the possible ways the universe could behave, only the behaviors consistent with the underlying symmetries are allowed. The universe does not freely roam through all possible structures. It is constrained to explore only the space of structures compatible with its symmetries. This is why patterns repeat. The same symmetry operating at different scales produces the same geometrical signatures at those different scales. The branching pattern of the cosmic web and the branching of a lung both arise from systems following the path of least resistance under some conserved quantity, whether momentum, energy, or entropy. The underlying symmetry is the same. The result is the same shape. The most profound implication of Noether's theorem is not just that symmetry produces conservation, it is that the universe has symmetry at all. There is no logical reason why the laws of physics must be the same at every location in space, or at every moment in time. A universe where the laws changed arbitrarily from place to place would be internally consistent. It would simply be chaos. The fact that the laws are symmetric, that they look the same everywhere and always, is itself a deep and unexplained feature. And if symmetry is the foundation of all physical law, and the universe has symmetry built into its foundation, then the universe itself may be a mathematical structure rather than a physical one. That claim sounds extreme. A growing number of physicists are making it anyway. Max Tegmark is a cosmologist at the Massachusetts Institute of Technology. He has spent years developing what he calls the mathematical universe hypothesis. The core claim is this: the universe is a mathematical structure. Physical reality does not merely follow mathematical laws. Physical reality is a mathematical object, existing in the same sense that a triangle or a prime number exists independently of any mind that thinks about it. This is a stronger claim than saying physics uses math to describe nature. Tegmark is saying that the distinction between the mathematical description and the physical reality is an illusion. There is only the mathematics. The argument begins with an observation. Every property of every physical object that science can measure is a mathematical property. Charge, mass, spin, position, momentum. All of these are numbers or mathematical quantities. The electron is described completely by a small set of mathematical properties. Remove those properties, and there is no electron left to point to. The electron is its mathematical description, and nothing more. If every physical thing is fully described by mathematics, and the description is complete, meaning nothing about the physical thing goes beyond what the math captures, then the physical thing and the mathematical object are identical. The hypothesis has a striking implication. Every mathematically consistent structure exists as a universe. The one we inhabit is not special in kind. It is one mathematical structure among all possible mathematical structures. And the reason we find ourselves in this particular one is that only certain structures are complex enough to support observers. This connects to the fine-tuning problem from Chapter 4. The fundamental constants of our universe happen to be compatible with atoms, stars, and life. If every mathematically possible universe exists, this requires no special explanation. We live in one that works because observers can only exist where the conditions permit. Critics raise several objections. The hypothesis predicts an enormous number of universes we cannot observe, which some argue makes it untestable. and therefore outside the domain of science. Others point out that not all mathematical structures would be inhabited, and identifying which structures can support observers requires assumptions about what observers are, which is itself a deep unsolved problem. A different version of the same general idea comes from the physicist John Archibald Wheeler. He proposed that at its foundation, physics is information. Every particle, every field, every space-time geometry reduces to binary questions and their answers. He summarized this with the phrase, "it from bit." The universe is made of information, and physical objects are manifestations of information relationships. Recent work connecting quantum information theory to space-time geometry has given this idea mathematical grounding. Researchers have shown in specific models that the geometry of space-time can be derived from the entanglement structure of quantum states. Space emerges from information. Matter emerges from the relationships between quantum states. If the universe is fundamentally informational or mathematical, the patterns become expected rather than mysterious. Mathematical structures are full of self-similarity, power laws, fractal geometry, and symmetry. They are full of the very features that appear across every scale of the observable universe. A mathematical universe would naturally look like this, because mathematics itself looks like this. The pattern hidden in the universe may be visible because the universe is the pattern. And the most recent physics is closing in on precisely how that connection works. The bridge between quantum information and the geometry of space has been built, piece by piece. And what it reveals about the fabric of reality is more startling than almost anything else in this script. In 2006, physicist Shinsei Ryu and Tadashi Takayanagi published a formula that connected something from quantum information theory to something from the geometry of curved space. Their result related the entanglement entropy of a region in a quantum system to the area of a geometric surface in the gravitational space-time dual to that system. The formula was derived from Maldaceno's anti-de Sitter conformal field theory correspondence, the same mathematical duality discussed in the chapter on the holographic principle. Entanglement entropy measures how strongly two regions of a quantum system are entangled with each other. It is a purely information-theoretic quantity. Geometric area is a property of curved space-time. Ryu and Takayanagi showed these two completely different-looking quantities are equal. This was remarkable. Space-time geometry and quantum entanglement are not just analogous. In the mathematical framework where this result holds, they are the same thing described in two different languages. The implications were developed rapidly. In 2010, Mark van Ramsdonk published a paper arguing that entanglement is what holds space-time together. He showed that in the holographic framework, if you reduce the entanglement between two regions of the boundary quantum system, the corresponding space-time region develops a bottleneck and eventually pinches off. Remove entanglement entirely, and the space-time splits apart. Space-time connectivity is held together by quantum information. Van Ramsdonk's argument was initially received with skepticism. The paper was rejected by one major journal before appearing elsewhere. Within a decade, it had become one of the most cited papers in quantum gravity, because subsequent work continued to confirm and extend its conclusions. The framework, now called quantum error correction and space-time geometry, has grown from these seeds. Researchers, including Ahmed Al-Maheri, Shi Dong, and Daniel Harlow, showed that the holographic encoding of bulk space-time information in boundary quantum states has the structure of a quantum error-correcting code. The same mathematical structure used in quantum computing to protect information from errors turns out to describe how space-time is encoded in quantum information. This connection is confirmed within the mathematical models where it has been derived. Whether it extends to the real universe, which has a positive cosmological constant rather than the negative one used in the anti-de Sitter framework, is an open question that drives a large portion of current research in quantum gravity. But even as a result within a specific model, it is transformative. It means that the geometry of space, the thing that gives the universe its shape and allows distances to exist, is not a primitive feature of reality. Space is built from the entanglement between quantum degrees of freedom at a more fundamental level. The three-dimensional universe you inhabit may be a structure that emerges from a layer of quantum information that has no obvious geometry at all. Distance, area, volume, and the curvature that we experience as gravity would all be derived quantities, features that appear at a certain scale of description but dissolve into pure information at the deepest level. Every pattern discussed in this script would then be a pattern in information. The fractal structure of the cosmic web, the golden ratios in spiral galaxies, the Fibonacci numbers in pine cones, the axis of evil in the oldest light, all patterns in a universe whose fundamental fabric is quantum entanglement. The clearest sign that this is pointing towards something real is the fact that the deeper physicists look, the more consistent and precise the pattern becomes. The universe is not hiding the pattern. The pattern is becoming more visible as the tools improve. In the early 20th century, astronomers debated whether other galaxies existed. The Milky Way was thought by many to be the entire universe, with the fuzzy patches called nebulae being nearby gas clouds inside it. Edwin Hubble settled the debate in 1924 by measuring the distance to the Andromeda Nebula and showing it was nearly 1 million light-years away, far outside any reasonable boundary for the Milky Way. The universe turned out to be vastly larger than anyone had estimated. Each generation of better instruments has expanded the picture, and each expansion has revealed more pattern, more structure, more regularity where randomness might have been expected. The first redshift surveys mapped hundreds of galaxies. The Sloan Digital Sky Survey mapped hundreds of millions. The Dark Energy Spectroscopic Instrument, currently operating, is measuring tens of millions of galaxy positions and redshifts with an aim to map the universe's expansion history in unprecedented detail. The Vera Rubin Observatory and the Euclid Space Telescope are adding more dimensions to the map. The James Webb Space Telescope is reaching back to galaxies formed within a few 100 million years of the Big Bang. With every improvement in resolution, sensitivity, and coverage, the patterns previously measured at coarser scales have held up. The barium acoustic oscillation signal remains measurable and consistent. The power spectrum of the cosmic microwave background matches its theoretical prediction more precisely as satellite resolution increases. The fractal properties of the cosmic web appear at the same dimension, whether measured with survey data from the 1980s or from datasets 1,000 times larger. Patterns that could have washed out at higher precision have sharpened instead. This is not guaranteed. Many scientific patterns that appeared robust at low resolution have dissolved when examined more carefully. The face on Mars, observed as a compelling feature in low-resolution Viking spacecraft images in 1976, disappeared entirely when higher-resolution cameras photographed the same landform later. Patterns in noisy data often vanish when the noise is reduced. The patterns in the universe have done the opposite. The Planck satellite's measurement of the cosmic microwave background spectral index is 3 times more precise than the Wilkinson microwave anisotropy probe's measurement, and the value sits in exactly the range inflationary quantum mechanics predicted. The large-scale galaxy alignments found in smaller surveys persist in larger ones. The cellular structure of the cosmic web becomes more detailed and consistent as survey volume grows. This behavior has a name in statistics. Signal-to-noise ratio improves. If the pattern is real, improving the instruments makes it clearer. If the pattern is a fluctuation or artifact, improving the instruments makes it disappear. The patterns discussed in this script have been improving, and that trajectory creates an uncomfortable implication. If the pattern becomes clearer every time the instruments get better, there is a limiting case to consider. At some level of precision, If the pattern continues to sharpen, the regularity of the universe will exceed what any unguided random process can plausibly produce by chance. Physics has not reached that line. The standard model with inflation and dark matter still explains the major features without invoking anything beyond known physics. But the margin between, explained by known processes, and requires something additional, narrows with every dataset. The pattern is real. It is consistent. It spans every scale from quantum fluctuations to the largest structure in the observable universe. And the closer you look at it, the harder it becomes to draw any comfortable boundary between what discovery is and what something else might be. The patterns are real. The cosmic web mirrors the human brain in measurable statistical ways. The universe branches like a lung, spirals like a galaxy, tiles like a dragonfly wing, repeats like a fractal, and resonates like a quantum field. Its fundamental constants are set with precision that defies intuition. Its oldest light encodes quantum predictions made before the measurements existed. Its empty voids follow mathematical scaling laws. Its galaxy spins align across distances that no known force can bridge. Its space-time geometry may be assembled from quantum entanglement. Across 32 chapters of confirmed observations, measured properties, and rigorously tested predictions, one thing has not appeared: a simple, complete explanation for why all of this is one coherent pattern. Physics offers partial explanations for each piece. Gravity explains the cosmic web. Quantum mechanics explains the fluctuations. Symmetry explains the complexity. But no single framework ties all of these together into one explanation for why the universe has the character it has: regular, self-similar, precisely tuned, mathematically structured, all the way to its foundations. 3 broad interpretations exist, and choosing between them honestly requires acknowledging what each cannot explain. The first is coincidence extended by selection. The universe is vast, and the portion accessible to observation is the portion where conditions allowed observers to form. We see patterns because pattern-forming conditions are the ones that produce minds capable of noticing patterns. The regularity is real, but it requires no special explanation beyond the fact that a universe capable of producing observers is the kind of universe observers will find themselves in. The problem with this interpretation is that it does not explain the precision of the mathematics. The anthropic principle explains why the constants must permit complexity. It does not explain why the same mathematical structures appear at every scale, why the cosmic web mirrors a brain, why Fibonacci spirals appear in galaxies and pine cones, why prime number spacing matches quantum energy levels. These cross-scale correspondences go beyond the conditions necessary for life. The second interpretation is that mathematics is the fundamental layer of reality, and the patterns are expected features of a mathematical universe. Physical objects are mathematical objects. The universe's coherence is the coherence of a mathematical structure, which is by definition consistent with itself at every scale and in every domain. The pattern is not a clue pointing towards something external. The pattern is the thing itself. The third interpretation is that the precision and coherence point toward a form of design. This is the territory where science, philosophy, and theology overlap, and it is the only territory in this script where confirmed observation cannot resolve the question. No instrument can measure a designer. No experiment can test for intention. But precision is a fact. The source of the precision is not within the reach of the scientific method. What science can say is this: the universe has a pattern. The pattern holds from the smallest measurable scale to the largest mapped structure. The pattern is mathematical in character. It becomes clearer as instruments improve. It appears in systems separated by every possible difference of scale, medium, and origin. And no current theory fully explains why the pattern is there. That gap between what is measured and what is understood is where the next physics will have to live. Every great expansion in human understanding has come from refusing to accept that the pattern was accidental. Newton refused to accept that apples and planets were unrelated. Einstein refused to accept that space and time were independent. The physicists working now on quantum gravity, on the string landscape, on the emergence of space-time from entanglement, are refusing to accept that the pattern across all scales is a coincidence. They may be right. The universe appears to be trying to tell us something. The question is whether we are finally close enough to hear it.